Hi students. So let's go to practice, fluid domain practice. What you should know that uh, like other domains, modeling in the isothermal liquid or IL requires both a solver configuration and a domain specific reference. That's a domain specific reference, which is in this case it is a reservoir uh, IL like isothermal liquid block. The reservoir block represents an infinite volume of liquid. This is represent an infinite volume of liquid at a specified pressure. By default, this pressure is the atmospheric pressure. In addition, you can specify the properties of the liquid in your network using something we call it the isothermal liquid properties. This is the isothermal liquid properties in which you specify the type of liquid you are using in your network. So by default, it's water. Okay, so this task is to ask you to add them. So I added them. You can simply look for them like this, like writing as always reservoir. Okay, reservoir IL. Okay, IL. Let's go drag a bit down. This is the reservoir IL. I think you saw it, right? Reservoir. Okay, here it is. And it's the same for the other stuff, which is the isothermal liquid property. If you write isothermal liquid property, you'll find it. Okay, we don't need it one more time. Let's go to task 2. Well, task 2 asks you to add a pressure source. Let me, before reading it, let me try to add a pressure source and see what they want from pressure source. Okay, add a pressure source to your model. Here you go. This is the pressure source G. Okay, it is in purple. So right. And change the source type to constant. Add a pressure source. You change the source type to constant and set the pressure differential to the following. Pressure differential to, those are value defined by MATLAB. And it has port A and port B. Well, is it that the pressure source that I want? Let's make sure that's the one, or maybe you have another one. Let's see. If I go to sources, it seems just the pressure source that I want. This is the one. IL, not G. Isothermal liquid. So this is the one. Good. So that's what I'm looking for. And not this one, okay? So now if I click on it, again, double click on it, they are saying change the source type to constant. Okay, and the pressure differential to rho times G times H, height of the reservoir, and the unit is Pascal. The unit is Pascal, and those parameters are defined in the workspace, so you don't need to bother yourself in defining them. Connect port A to the reservoir. Connect both the solver configuration block and the isothermal liquid properties block to your network. So by default it is a water. Okay, this is the step now. Good. All right. Let's read a bit about a pressure source, which is this one. Allow you to specify a pressure differential as we did between ports A and B. In this case, it's rho J H, right? Rho GH. The pressure can be specified by external physical signal. Can be specified by external physical signal, like in this case, okay, or by a constant value entered as a block. Now what we did is we take it as a constant value entered as a block, and we define it as this pressure differential rho GH. If we say it's controlled, look at it. If we say it's controlled, if I say apply, look, it will look like this one, controlled. But we change it to the source type to constant, remember? So now it will disappear and it becomes like this, okay? This simply is a task here, nothing more, just asking about this, as simple as that. All right, let's see on. A pressure differential drives water flow from high pressure to low pressure, of course. In the simple fluid circuit that you will construct here, water flows through a pipe driven by hydrostatic pressure. So the fluid through a pipe and driven by the hydrostatic pressure. Good. Let's see. Add a pipe and a second reservoir block. Okay, let me add a pipe, hydrothermal block, and I want to add a second reservoir hydrothermal liquid. Good. Set the pipe length to 20 meters. So pipe length is a 20 meters. And the cross-sectional area to the cross-sectional area, right? Let's see, where is the cross-sectional area? So not the pipe diameter, well here, okay, maybe pi 0.5/2 square, like if you are talking about circular diameter, in this case of 0.5, it's like of saying 0.5 pipe diameter. So then in this case this cross-sectional area is pi r square, and the hydraulic diameter to 0.5. Pipe diameter and the hydraulic diameter to 0.5. Okay. Some other things maybe, but this is the hydraulic diameter, probably pipe diameter, cross-sectional area, it's a circular. It's alright. If we said custom, I don't think this is will work. Okay, we put it custom. etc. It's the same, actually same, it returns to be the same. But let's put it custom so that in this case we are defining our area ourselves. So pi then times 0.5 over 2 square, so that we follow the model exactly. But we don't need that. As it was doing, it was exactly the same. Hydraulic diameter 0.5. All right. Connect the inlet of the pipe port A to the pressure source. Okay, they are connected now. And the outlet port B to the new reservoir. Good. So it sounds logic what we are doing. Okay, a pressure differential drives water flow from high pressure to low pressure. This is the pressure differential or pressure source with a differential pressure of rho GH. Drive in this simple fluid circuit that you will construct here, water flow through a pipe driven by a hydrostatic pressure. That's the hydrostatic pressure, the static pressure, and here is the pipe, so which has a 20-meter length and an area, etc. Okay. Task. So it seems here something wrong in the assessment criteria. Does the following log have the correct parameter? Pipe IL has a pipe length of 20, hydraulic diameter of 0.5. Let's see. Pipe length of 20 meter, okay. Hydraulic diameter of 0.5 meter, okay. And cross-sectional area of pi times 0.5 over 2 square meter square. It is right. Why they are saying it's wrong? Okay. Does the following blocks value match the plotted requirement? So why it is wrong, even so we know it is right? I mean, pipe length is, as they said, right, 20 meter, and the cross-sectional area is pi 0.5 over 2 square. All right, and sure, if you need to, yeah, it seems right. I don't know. And the hydraulic pressure, hydraulic diameter is 0.5. The equivalent of it is to say circular, well, and simply precise the pipe diameter. And this is also work. Both are right. I mean, you can work this way. Let's see. Let's run it. If you have error, caused by empty object name found. Okay, pipe length of 20, and well, I can keep it custom, and that's what they are doing. So doing the same, and length of 0.5. All right. Now, if I submit it, it seems, well, let's see what they are doing here as a solution. In case you press in see solution or hint, you may find something now. Be sure to add the pipe from the isothermal library block. Okay, it seems this is not the pipe we want. Pipe IL, but it seems like you have another pipe. Like, look, this is to be something different. Be sure to add the pipe from the isothermal liquid library. So here it is. Not the first, not this one, is this one. All right. So that's what caused the problem. Now when you click on it, it makes more sense saying pipe length of 20 now, cross-sectional area of pi times 0.5 over 2 square would, it makes more sense, and hydraulic diameter of 0.5. All right, so here we go, as simple as that. Yeah, so of course that hint help us a bit. So now resetting so that we can submit again. A bit slow, yes, because it's online. Yes, we want to access the submission before going to task 4. Okay, please give me access to the submission again. Okay, let me run as on all cases, but I don't think I should access the submission somehow. It is exactly the same, but I need to still, this is still giving wrong because I didn't submit it. And it seems like I'm unable to press submitting. I'm resetting and waiting, but it seems it will take time. But here we go, that's the essential thing. Let's do task 4 in your, but unfortunately I wasn't able to submit task 3. In your hydroelectric power model, some of the water leaving the pipe will go to the water wheel and some will be diverted to the overflow reservoir. Okay. All right. So for now, you will build a fluid circuit that splits the flow between two outlet pipes. The flow that comes from here will be split between two output the flow that comes from the source will be split between two output part or two output pipes. Create two new copies of the pipe and connect them to the outlet of the original pipe. So pipe, pipe, and pipe. Okay. All right. Okay. Delete the reservoir at the outlet of the pipe. Delete the reservoir IL at the outlet of the pipe. That's what they said, to delete it. Create two new pipes of the pipe, new copies of the pipe, then connect them to the outlet of the original pipe. Such that the flow splits them between two. Add two new reservoir blocks and connect them to the open ends of the pipe. Okay, they ask you to add two reservoir here and connect them there to the open end of the reservoir. Okay, so here you go, you add reservoir to here and you add B to here. Okay, so this is the step. Let me go to 3 to see if I can submit. So then it seems I cannot submit. It's all right, but anyway, so this will be your task 4. Good.